about, I'm going to talk a little bit about the binomial model today. So some of this is going to be what I went over in class for those of you who are absent. So suppose you have 100 computer chips and the probability of a chip being defective is 0.02. What's the probability that 5 chips will be defective? Now this is different than what we did, same idea from the problem with the computer chips, and the probability of being defective is 0.02, but this time it's not geometric. So remember that when you have a geometric distribution, you're always answering the question, how many trials until the first success? Well, this is different. Now it's still Bernoulli because you still have 2 outcomes, success or failure. The probability of success is the same for each trial at 0.02, and we're assuming here that each computer chip is independent from the other, which makes it Bernoulli. But this time we have a fixed number of trials. N equals 100, and we want to know the probability of exactly 5 successes. So when this is the case, when we have a fixed number of trials, that makes it binomial. So this is a binomial model. Now, if you go through, and I talked about this in class, but we know this is the, we have this 0.02 right here is, to the 5th power, is my 5 bad chips and the 95 good chips. So when you multiply that together, you don't get the answer because there are a lot of different ways you could have, if you have 100 chips, there's a lot of different ways you could have 5 bad ones. So the first 5 could be bad and then the next 95 good. Maybe the first one's bad, the next few are good, then a bad one. And so we have to know how many ways there are to arrange the 100 chips so that 5 of them are bad. So I talked about this in class. We can do something called 10 choose 5. And when you do that, this is available on your calculator, but the formula for that is 100 factorial over 5 factorial times 95 factorial. So remember what factorial means: 100 times 99 times 99 times 98, all the way down to 1. I stopped here and did 95 factorial so I could cancel out the denominator. So when you work this out, you get 75,287,520 different ways that you could arrange those. So you do have to multiply by that, and we get our answer of, if you have 100 computer chips and you want to know the probability of getting exactly 5 of them to be bad, remember the success in this case was a defective chip, then you get 0.0353. So there, we have already seen a normal model with parameters mu and sigma. We've seen a geometric model with the parameter of p, the probability of success. Now we have the binomial model with n representing the fixed number of trials and p representing the probability of success. The formula for the binomial model, the probability that x equals some value k, you're doing this n choose k, p, the probability of success to the kth trial, 1 minus p to the n minus k trial. So for my example, we would have the binomial 100, n is 100, and p is 0.02. So we're looking for the probability that x equals 5. So we have 100 choose 5, 0.02 to the 5th, 0.98 to the 95th. You can actually do this on your calculator, just like we did the geometric PDF. We can do binomial PDF, enter in the values, and come up with that probability. So if we go second, distribution, we want binomial PDF. So we have 100 trials. P is 0.02. We wanted 100 choose 5, so we want 5 successes. And there's our answer. Okay, so binomial PDF. So what if instead I asked for the probability that I get no more than 8 defective chips out of 100? I still have a fixed number of trials, 100 trials, and I want no more than 8 defective chips. Well, no more than means I have less than or equal to 8, but no more than. So I'm looking at the probability that x is less than or equal to 8. Remember, just like for geometric, if we have binomial, with less than or equal to, we can use the CDF. That's the cumulative distribution function. So in that case, if I go second distribution, and I'm going to go up here to Binomial Cdf, and we have 100 trials. P is 0.02, and my value of x is 8. Notice you need to make sure you're on the same, or you're on the correct one that you want, because these inputs are no different for PDF, but the answer will be quite different. So this is my answer, so I get 0.9998 if I round to 4 decimal places, and that is that's what you do if it's less than or equal to. Okay, so what if we ask the question, what's the probability that at least 5 chips are defective? Well, at least 5 means there could be 5 or there could be more, but there's not less. So I'm looking at the probability that x is greater than or equal to 5. Now, note this is still out of the 100. So we can't use CDF for greater than or equal to. Remember that CDF always has to be less than or equal to. So I have to switch this around. So it's going to be 1 minus the probability x is, and we're going to switch it to less than or equal to. Now, this time, because the 5 is included here in my original question, I cannot include the 5 here, so I drop it down to a 4. If this had been strictly greater than 5, then this would have been less than or equal to 5. So you have to stop and think about that when you are dealing with a discrete distribution. Then you can just evaluate this on your calculator, which I did do that. Oh, looks like I got rid of my calculator there. But and evaluated that answer. So, oh wait, I think I may have did not subtract that. So hold on just a second. Let me verify this. Okay, so I had forgotten to subtract from 1. So the binomial CDF, when we fill that in for the probability that x is less than or equal to 4, we get 0.9492. Subtracting that from 1 gives us 0.0508. All right, just like we had a mean and standard deviation for the geometric, we also have a mean and standard deviation for the binomial. So the mean for the binomial model is n times p. The standard deviation for the binomial model is the square root of n times p times 1 minus p, which some textbooks will call the 1 minus p, they'll call that q. That's the probability of failure. So remember in our example, the success was bad. So for the computer chip example, with n being 100 and the probability of success being 0.02, then our mean of our binomial model would be 2, which means that's our expected number of bad chips in our set number of trials of 100. Our standard deviation, when you fill that into the formula, you get 1.4 chips. These are 2 formulas that you can find on your yellow sheet, which is the same formulas that are available to you on the AP exam. Okay, so now it's time to start looking at some examples. You might want to have your book out as we go through this. So if you want to pause it, take a look at page 399, number 13. So it says, assume that 13% of people are left-handed. If we select 5 people at random, find the probability of each outcome described below. So they tell me that P, probability of success, is 0.13, and we're selecting 5 people, so n equals 5. The first question asks, what's, in words here, I wrote it out in symbols, it says the first lefty, we want to find the probability that the first lefty is the 5th person chosen. Well, we're looking at the probability that x equals 5, okay? But the thing you have to think about in this case is this is geometric because we're looking at, we are looking at the probability of the first success. The first lefty is the 5th person chosen. I should have written the G of the 0.13. This is my notation because remember, for geometric, we have the probability of success. Here was 0.13. So that means we had 4 people who were not left-handed, and then the 5th person was. So you might be doing a problem like this one is, where the first part is, one part might be geometric and then the next part might be binomial. Part B says there are some lefties among the 5 people. Well, that's binomial. That's going to be a binomial model, the probability that we have some lefties. So that means one or more of the people are lefties. Okay, so we could do that with 1 minus the probability of none, because the only thing that we're not going to include is that there are no lefties. And so this is binomial. We have a set number of trials. P is 0.13. So we actually can figure out, you can do this on your calculator with Binomial PDF and with 0, and then we come up with that answer, and we get 0.5016 is the probability that there are some lefties. The next question says, the first lefty is the second or third person. Okay, this is geometric because notice it says the first lefty, so that's your hint, is the second or third person. So this is going to involve addition as well. So this is asking the probability that x equals 2 or the probability that x equals 3. So you can actually use your calculator, but for geometric I don't usually do that. It's easy to do just to write it out. If the second person was the first lefty, then that means the first person was right-handed. So we have this product. This would represent that the third person was the first lefty. You would multiply those products out, add it together, you get 0.2115. You could also do this with the geometric PDF. If you use this information here on your calculator, this is P, this is the value of X. And you would do both of those, and then when you then you would come up with that answer. And so that's another possibility if you wanted to use your calculator. I think it's easier to just kind of work it out. Part D says that there are exactly 3 lefties in the group. So we are still dealing with binomial, because now it's not the first, you don't see the first success anywhere in that. So out of the 5 people, we want to know the probability that there are exactly 3 lefties. So we're dealing with binomial, so that's our model. I want to know the probability that x equals 3. Now you'll notice that I put the formula, I used the binomial formula on this one, but you could also, and you could work it out, or if you do the binomial PDF on your calculator, you will get 0.0166. The next question says there are at least 3 lefties in the group. So you have to think about what that means, at least. Well, that means there could be 3 or more, but not less than. So the least is 3. This is greater than or equal to, can't do CDF for that. I'm going to have to do the 1 minus and switch the sign around. Because the 3 is included here, I do not include the 3 here, which is why I dropped it down to a 2. So then you're going to use Binomial Cdf with a 2. Don't forget to subtract that from 1, because we have 1 minus that, and we'll get our answer of 0.0179. That's the probability that there are at least 3 lefties in the group. Part F says there are no more than 3 lefties in the group. Again, this is binomial, and this time there's no more than 3. That means there's 3 or less, but no more than. And this one is just a binomial CDF problem. You don't have to worry about subtracting, but you should have those symbols there. Now, what I showed next here on this one, we only have 5. This one we have a set number of trials. We had 5 people that we were looking at. If you set your calculator up, and let me show you how to do this. If we go to our stat list, and in L1, I'm going to put down all the possibilities for the number of lefties I might find. From 0 to 5, because we're only choosing up to 5 people. Then I'm going to define L2 as, I'm going to do the second distribution, and I'm going to define it as binomial PDF. And put in 5 trials. The probability of success is 0.13. And my X value, I want my calculator to look for them in list 1. and I get these values. These are all my PDF values. So I can kind of do them all at once and have those PDF values. Well, I don't have to stop there. If I want the CDF values, I can do the same thing. Second distribution, and now I'm going to go up to the binomial CDF, put in 5 trials. Probability of success is 0.13. Whoops, didn't take the point. And I want this to get my values also out of list 1. And those are going to be all the CDF values. Notice that by the time I get to the end, less than or equal to 5, it's a 1 because I only had 5 people. So, so the CDF will always be that for binomial. That's different from geometric. So that is helpful. If you take a look at number 15, still the 5 people, whether or not they're left or right-handed. So the question is, how many lefties do you expect? Well, we still have 5 people, so n is 5. The probability of being left-handed is 0.13. It is binomial with 5 and 0.13. When you see the wording, how many lefties do you expect? That's talking about expected value, which means it's the average or the mean. So we need this formula. So mu sub x equals n times p equals 5 times 0.13 equals 0.65. Now, you might argue, how can you have 0.65 of a person? Regardless, that's the value that you would report for the mean of the binomial model. Then the next question says, with what standard deviation? So you're going to write out that formula, you're going to substitute everything in and evaluate it, and you get your standard deviation. Part C says, if we keep picking people until we find a lefty, how long do you expect it will take? Now this all of a sudden is shifting because they're saying, how many do you think it will take until we get our first lefty or our first success? So now all of a sudden this is switched to a geometric model with a probability of success of 0.13. And if you remember, the mean for the geometric model is 1 over p. So we get approximately 7.7 people. So if you go ahead and look at problem 17, 17 says, suppose we choose 12 people instead of the 5 chosen in exercise 13. So we still have the probability of success of being left-handed, 0.13, but this time n is 12 because that's our sample size, still a set number of trials. So it says find the mean and standard deviation of the number of right-handers. Right-handers in this group. So all of a sudden it switched to right-handers. So our probability, so my problem is wrong. So let me pause this and redo. Oh, I'm glad for the pause button. Okay, so I fixed it, and it's a binomial. N is 12. Probability of success, since we're looking at right-handed, it's 0.87, 1 minus 0.13. And see how important it is to read the problem carefully. So the expected number of right-handers in the group out of the 12 times 0.87, using that formula, we get 10.44. And the standard deviation, when you substitute the values into the formula, you get 1.1650 if you round to 4 decimal places. Part B says, what's the probability that they're not all right-handed? That means that there's at least one lefty. They're not all right-handed. So sometimes these are hard to kind of think through. The probability that they're not all right-handed is 1 minus the probability that they are all right-handed. So I went with that idea and thought about it in words first. So then that would be 1 minus the probability that x equals 12 using this particular binomial model. So the probability that all 12 of them are right-handed is 0.1880. So then the probability that at least one, that not all of them are right-handed, is 0.8119. Then in part C, it says, what's the probability that there are no more than 10 righties? Well, no more than 10 righties means that there could be 10 or there could be less, but no more than. So this is just specifically a binomial CDF problem. So you can use that and evaluate it on your calculator. Then the last couple parts. Part D asks, what's the probability that there are exactly 6 of each? Okay, well, if there's exactly 6 of each, that means there are 6 right-handed and there are 6 left-handed. Well, since if they're not right-handed, they're left-handed, then all I really need to know using the binomial model is that the probability that x equals 6. 6 right-handers guarantees that there are 6 left-handed. So when you evaluate that, you get 0.0019. And then in part E, what's the probability that the majority is right-handed? Well, what does majority mean? That means more than half. So more than 6 are right-handed. Well, I want to use CDF, but I can't do it for greater than, so I have to switch this around. Because the 6 is not included with this question, the 6 has to be included when you flip it around to less than or equal to. So I'm going to use the CDF on my calculator, and when I subtract it from 1, I get 0.9978. So those are some examples of how you can use the binomial model. Notice that there were some geometric model problems kind of filled in there. I'm going to post an assignment, but for sure you need to watch this video and then start working on that assignment. I'm sure that you will have some questions, but that's going to be your assignment for today.